is elementary kinetic theory. It includes 5 chapters. Actually, it cannot be possible to take the class even we cannot complete a one two deriving expressions. To derive 2 expressions, it will take almost 1 hour. So class is not possible. Only it is a doubt. Your class is the doubt clearing class. You can you take a lesson on a whole of the courses or a block, and you discuss where you face the problem. So in the second class, in the we'll let you learn about the block 2, about the thermodynamics. So go through this block 2 part and try to ask question where you face the problem, right? Now see, we'll first chapter in the first chapter of the elementary kinetic theory block is ideal gas. I'll go through block 1. If some problem, okay. The BPHCT-135 is your thermodynamics and statistical mechanics. Are you able to see the screen?
No, sir.
No, sir.
Screen is not. Are you not to see?
Sir,
Some technical problem.
sir, are you representing any scene, sir, or are you presenting any scene? Now we are able to see you, but there is no screen. We are not able to see anything. Only we see you here.
Okay.
There is a screen presentation option is there, sir.
Screen presentation option. I'm presenting through screen. So I'm bringing to. Okay.
Go to the sir start presentation, then start now, then it will come, sir.
Something.
Share screen, sir. On the right side, 3 vertical lines are the points are there. Then share screen. If you put that share screen, then start now it will come, sir. After that it will start.
Okay. Okay. I'm facing some problem now. Okay. Are you able to see?
Just a minute, sir.
No.
No. We are presenting to everyone. You click on. I have to you see options classroom RC BBSR U and RC classroom RC Bhubaneswar your presentation. Okay, you pin on that.
But there is no option of for the screen, sir. There,
तुमको देखा?
Yes, sir, I got it, sir. Hello. Hello, I got it, sir.
Okay, got
Yes,
it.
sir, I got it. I can see the
Second टा
screen.
देखो. हाँ, explain. आउन मनु टे कही दे उदय.
सर आपनको जो फोटो आसे सर फोटो ऊपर गोटे पिन रो सिंबल थिबो ताको क्लिक करले आसला
ଆସୁଛି
ଆସିଲା.
sir. ଏବେ ସ୍କ୍ରିନ୍ ଟା ଆସୁଛି. You are presenting to everyone. ଖାଲି ଯା ଲେଖା ଯାଇଛି.
सर खाली सेटा देखा जाउछ
हाँ, ओके एटा बर्तमान देखा जीवो.
ओके सर
देखा गला कि
ଆସୁଛି sir, ଆସୁଛି.
यस सर देखा गला
देखा गला.
यस सर
Okay, so I mean because you see it we have 5 chapters and we have to complete in one class. Just we have to touch the summary part of the chapters, otherwise it will be difficult. I think once you touch the summary part, then it will be easier to start learning. I think so.
Okay.
Right?
Sir, excuse me.
Okay.
Sir, excuse me.
Okay.
Sir, this is a request, sir, from my side. Sir, if you will deal through that means if you will discuss the questions, the assignment questions, then it will be also, sir, better. So that we will write the assignment also. जो assignment question sir ମିଳୁଛି ଯଦି ସେଇଟାକୁ ଯଦି discussion ବି କରିପାରିବୁ sir ତାହେଲେ ସେଟା ବି ଭଲ ହବ ତାହେଲେ ଆମେ ଟିକେ ଲେଖିପାରିବୁ ତାର assignment answer sir.
Okay, in the next class, I am not prepared for that. In the next class, we'll try to we have first collect the assignment questions, but I have to prepare also about the assignment questions. Okay. So it is not possible now since assignment questions are not collected. Okay. So
Okay.
today we'll complete our class. Try to understand this. With this, we start with the first chapter, elementary kinetic theory, block 1. So the first chapter is your ideal gas, and in the ideal gas, first you will learn about the basic concepts of the kinetic theory of gases, and basic kinetic theory based on 9 postulates that this every gas consists of large number of similar molecules, and the molecules are considered as the point masses. They are treated as elastic spheres, hard elastic spheres. Hard elastic spheres. So and they collide with each other elastically. Ideal gas is elastic collision, and when we will go to the real gas where actually the things are happening, that is the collision is not elastic. In elastic collision, total kinetic energy and total linear momentum remains conserved. Then before collision, the total kinetic energy and total momentum must be equal to those after collision. Okay, so this collision is elastic and they travel along a straight line in between two collisions, and the dimension of the particle is negligible in comparison to the distance they travel between the two successive collisions. So on the basis of these assumptions or postulates, we can say, of the kinetic theory, all these things are developed. I think we first develop the pressure exerted by an ideal gas on the wall of the container. When the particles bombard with the wall, if you take some gas inside a container and the particles is random motion, the kinetic theory basically based upon that all the molecules are in random motion. The velocity is ranging from 0 to infinity. That means all possible velocities They travel randomly in possible directions also. So the pressure exerted by an ideal gas on the wall of the container, that we can, it's a derivation, and that found to be 1/3 of rho v square bar, where rho is density of the gas, and v square bar the average mean square velocity. Mean square velocity means it is the average of square of velocities of all the molecules. And from this expression we can derive the kinetic interpretation of temperature, or the average kinetic energy of a molecule found to be P by 2 kBT. Kb is the Boltzmann's constant, which can be written as the gas constant by Avogadro's number. So similarly, the molecular speeds. In molecular speed, we can derive different expressions for it is the mean square speed, RMS speed, and mean square speed is the average of the square of velocities of all the molecules, where root mean square velocity is square root of this, and we find that this v square equal to 3 RT by m, and v RMS equal to 3 RT by m square root. We can also derive from the expression of the pressure. We can derive, since the expression of pressure is derived on the basis of the assumptions of the kinetic theory, we can say that kinetic theory is applicable to all these things. Where then deduction of gas laws. So all the gas laws, Boyle's law, Gay-Lussac's law, Paul's law, Avogadro's law, these also can be derived from this expression of pressure. And we know that in the case of Boyle's law, the pressure product of pressure and volume of the gas is constant. At constant temperature, the PV equal to constant. Similarly, Gay-Lussac's law, in a constant volume, the P by T, the pressure by temperature, is constant, or you can write the pressure is directly proportional to the absolute temperature of the gas. Similarly, in Charles' law, the volume of the gas is directly proportional to the absolute temperature of the gas. And at constant temperature and in equal volume, to different gases, they contain same number of moles of gas, that is Avogadro's law. Similarly, law of equipartition of energy. Law of equipartition of energy says how the energy is divided yet in thermal equilibrium. Thermal equilibrium, when the system and surrounding at the same temperature, we can say the system is in thermal equilibrium with the surrounding. The energy of a system, you can say a dynamical system is divided among all the degrees of freedom equally. The energy divided equally among all the degrees of freedom, and we can find out the energy, kinetic energy per molecule per degree of freedom is found to be half kT, where K is the Boltzmann's constant, T is the absolute temperature of the gas by molecule. Similarly, about the degree of freedom, can say how many independent coordinates are required to specify the position of a particle. Okay, if it is a monoatomic particle, it needs 3 degrees of freedom. Okay, here only linear motion is possible, when linear velocity can be resolved into 3 components, that is x, y, and z in space. So a monoatomic molecule has 3 degrees of freedom. Similarly, if we go to diatomic molecule, then diatomic molecule possesses the linear motion, and also there is a rotation about the axis joining the particles. Okay, joining the particles. Diatomic molecule means the molecule contains two atoms, monoatomic one atom. So two atoms, they are connected with the line, and this has to be taken as the axis, and the rotational motion, again the rotational velocity is, or rotational energy is divided into two. So 3 degrees of freedom are required, 3 for translational motion or linear motion, and 2 degree of freedom required for for rotational motion. That is why the diatomic molecule have 5 degrees of freedom. Okay. Similarly, also degree of freedom of diatomic molecule depends upon the temperature. If the temperature is very high, then in addition to translation, translational and rotational motion, also vibrational energy, where vibrational energy is any problem? Where vibrational energy, anyone is unmuting? Shilpa Marana, Shilpa Marana,
See, see. Again, sir, sir.
please
Yes, sir.
unmute your microphone.
Yes, sir.
Everyone is requested also to put their enrollment number in the message box, right? Shilpa, you also do it.
Sir, which topic is this?
Thermodynamics and statistical mechanics. This is block 1. Block 1, elementary kinetic theory, right?
Ji, again.
Okay. Now we learn about the heat capacity. Manoranjan, Manoranjan, Uday,
Yes, sir.
audible? Screen is
Yes,
visible?
sir. No, sir.
Screen is not visible.
No, sir. I can only see you.
Sir, screen is visible, sir.
Okay. Somewhere this is online problem is this. Somewhere it is problem, somewhere not problem. Okay. You see, heat capacity is the heat required to raise the temperature of the body through 1 degree Kelvin or 1 degree centigrade. The same. So amount of heat required to raise the temperature. If delta Q amount of heat is required to raise the temperature of the body, whole body or whole gas by delta T temperature, delta T, then for unit temperature, the heat required will be delta Q by delta T. Now see, specific heat capacity is for unit mass. The amount of heat required to raise the temperature of the unit mass of the body or substance through 1 degree centigrade. That is why a mass is divided. If m is the mass of the body and we delta Q by delta T heat for whole mass through 1 degree centigrade, then for unit mass, the mass has to be divided. That is why we put there 1 by m with delta Q, delta T. And the specific heat at constant volume, you can write CV. Okay. the amount of heat required to raise the temperature of unit mass of the gas by 1 degree centigrade at constant volume. Similarly, also for constant pressure, at heat required to raise the temperature by unit mass by 1 degree centigrade for at constant pressure. Cv, Cp. Since the molar specific heat is the amount of heat required to for 1 mole. Amount of heat required to raise the temperature of the body through 1 degree centigrade of 1 mole of the substance, and that is found to be N is the number of moles. If N moles of gas needs delta Q by delta T heat, then 1 mole is required 1 by N into delta Q by delta T. If you take it the molar specific at constant volume, then you have to heat it at constant volume. For constant pressure, you have gas at constant pressure, and this is found to be related to the degree of freedom. What is the expression of Cv? That is F by 2 into R. F by 2 into R. F is the degree of freedom and R is the gas constant, right? Then Cp equal to, Cp equal to Cv plus R. That since it is required at constant pressure, because in constant pressure some work is done along with the expansion. So at constant volume no work is done. Constant volume means there is no expansion. So since no expansion, no external work is done. But while heating at constant pressure, you have to raise the temperature. Along with that, you have to do some work, because constant volume, when we heat, the pressure of the gas will increase. So to maintain the pressure constant, then you have to expand. So when expansion of gas takes place, there is some external work is done. Okay, so some Cp equal to Cv plus R, and F by 2 Cv is to F by 2 R, you have to plus another R, that will make you F plus 2 by 2 R. Then the ratio of the specific heats, molar specific heat, Cp by C gamma equal to F plus 2 by F. With this, the unit 1 is unit, as per my preparation, unit 1 is completed here. Now we'll enter into the unit 2, which includes molecular velocity distribution function. Okay, and the Maxwell and Boltzmann took some vital role in developing the distribution function for velocities of the gas. Since the molecules move randomly with the all possible velocities, therefore we need
सर फास्ट ब्लॉग रो किछि यूनिट रो किछि क्वेश्चन देथिले भलो हेथांदा
हाँ देख से कौन होची तमरो असाइन क्वेश्चन को आसुची तमरो टर्म एंड क्वेश्चन गुडा को ताकू लेखिबा टर्म एंड क्वेश्चन पाई की मु रखी छी अनदर ब्लॉक आल्सो यू सी देखि पारछो
यस सर
ओके
सर आम पाखे स्टडी मटेरियल एपर्यंत आसीनी सेति पई प्रॉब्लम होची यदि क्वेश्चन दे थांदा टिके असुविधा हेथांदा
अरे तमे ई ज्ञान कोश you search in Google e-Ganox. There you click for anyone, physics, either zoology or chemistry. All the syllabus are study materials are available online through e-Ganox. Okay. Now see,
thank you.
I will show you term and questions. We find though they have attached here, change in. I'll take in the 5th chapter a van der Waals equation of real gas term and questions. Now see, okay, there you have to use the for
हेलो सर आपण स्क्रीन
terminal
शेयर करछन्ते कि
share करूची terminal
सर मते
question
देखा जाउनी सर
देखाउनी
नो सर
ଦେଖା ଯାଉଛି
केमती
ନେଟୱାର୍କ
केमती
हटे
ହଁ ହଁ ସାର୍ ଦେଖା ଯାଉଛି।
ସାହାଯ୍ୟ କର ସେ ଜାଣି ପାରୁନାହାନ୍ତି କେମିତି ସାହାଯ୍ୟ କର ତମେ ଯେମିତି ଦେଖି
ସେ
ପାରୁଛ
ଉପରେ ଯୋଉ ପିନ୍ ଟା ଅଛି ସାରଙ୍କ ସ୍କ୍ରିନ ଉପରେ ଯୋଉ ପିନ୍ ଚିହ୍ନଟା ଅଛି ସେଇଠି କ୍ଲିକ୍ କଲେ ଆସୁଛି ତ।
मते आसुनी
ଆପଣ ସାର୍ କି ଲେଖାଯାଉଛି ଟୋଟାଲ ମେମ୍ବରରେ ଯାଇକି ସାରଙ୍କର ଦୁଇଟା ବାହାରୁଛି ଦୁଇଟାକୁ ପିନ୍ ଅପ୍ କରିକି ଦେଖନ୍ତୁ କୋଉଟା ଗୋଟାରେ ଆସିବ ସ୍କ୍ରିନ୍
ओके ओके
ଦୁଇଟାରେ ଗୋଟେ ପିନ୍ ଅପ୍ ଯାଇକି କ୍ଲିକ୍ କରନ୍ତୁ
ଯୋଉଟା ପ୍ରେଜେଣ୍ଟ ଲେଖା ହେଇଛି ସେଇଟାକୁ ପିନ୍ ଅପ୍ କରିଦେଲେ ଆସିଯିବ
ହଁ
ओके
ओके मनोजन जदि आम कहवा यू कैन इन द कमिंग क्लास यू कैन डिस्कस the terminal question. Okay, the terminal question. Now see, the problem comes and a problem directly come with the formula. No derivation is required. Okay, you can know which are also subjective questions easily. Since the study material is not available, you go through the e-Gyana course. I have downloaded it from the e-Gyana course. You see, we take a lot of strain to prepare this. So go through the e-Gyana course,
sir
download the study material.
sir
Okay,
sir
okay.
आमे किछि क्वेश्चन पचारि परिबु से स्टडी मटेरियल रो
हाँ तमे श्योर तुमे पढ़ी के आसी थिले ओ जगह रे तो प्रॉब्लम होउची आमे डिस्कस करि परिबा
ओके
एक्चुअली
सर
एटा डिस्कशन हबो किंतु वी टेक ए क्लास देखो जो जोटा को आमे कहूचे जे फोर्थ 1 includes 4 units and
yes sir.
we in general class we take at least 4 to 5 lectures for completing 5 to 6 lectures for
Yes, sir.
completing a unit.
Yes sir.
Complete a unit. But how can we complete the 4 units in 1 hour?
Yes sir.
That is difficult. So this is not the manual mode or traditional mode of class. This is the distance mode. So you have to prepare and ask questions where you face the problem. We may discuss it.
Yes
This
sir.
is the right. This is the right mode of teaching in case a ignore learning process.
हाँ sir.
Okay.
सर डू यू हैव एनी नोट्स ऑफ दिस ब्लॉग सर
No, I have not the note. I just summarize the things since it is a first class. The learners are not ready for prepare to ask prepare the whole block to ask questions. So that is why we summarize the thing and we write. Actually, it's a lot of time. It requires a lot of time. How can we are in the present mode in taking classes in our colleges and we find very time for preparation. So I only prepared summaries of the 4 unit to discuss. Let in the block 2 when the block 2 is the block 2 is your thermodynamic like it the 0th law and the first law, 0th law, first law for thermodynamics. So go through, try to download the BPHCT-135 study material from the e-Gyana course. Okay. Then go through it, try to go through it, then you are able to ask any question. Unless you have study materials, how can you ask questions? Study materials, you don't take a study on this material, how can you ask question? Okay, so let me compare today. We have only 20 minutes left and I have now 4 units to cover up. You see, Maxwell distribution law. This Maxwell distribution law, based on the 5 postulates or assumptions for expression of distribution of velocities. For expression of distribution of velocities, how the velocities are distributed. Actually, in kinetic theory, in the postulate of kinetic theory, we say that the molecules possesses velocities from 0 to infinity. But how many particles possesses a velocity in certain range? That is the distribution of velocities. You can say these many number of molecules possess velocity in this range. So we start with the assumption that gas molecules move with all possible velocities, no mass motion or convection current. Mass motion means when the mass will move in certain direction, that will give to convectional current. So that is called convectional current. Like in the heat wave in the summer, cold wave in the winter, these are the cases of convectional current. Somewhere the molecules from the hot region flow to the cold region to maintain the environmental equilibrium. So the molecules which are molecules from the hot region, they flow to the cold region, that is giving rise to the hot wave. आमे जा कहूचे झांझी पवन बहे खरा दिन रे. Okay, so say no mass motion. Then the x component of velocity is independent of y and z component. Since they are perpendicular, then x component of velocity is independent of y and z component. And the probability that a molecule selected at random has velocity component in the given range is a function of magnitude of velocity. That is very important. That molecule selected at random has a velocity component in the given range. Molecule has velocity component in the given range. This probability is a function of magnitude of velocity component and width of the interval. And what is the range? And magnitude of velocity component and width of the interval. Okay, now the probability is proportional. So the gas molecules have no vibrational or rotational energies. With these assumptions, Maxwell derived a distribution function. The expression of the distribution function is like this: dqn vx vy vz. These are the component of velocities in x, y, z direction. N equal to aq into e to the power minus b v square dqv, where ab their constants to be determined. Constants to be determined. So Maxwell, now see, dqn vx vy vz, These are the number of molecules having velocity component lying between Vx to Vx plus dx, that is in x direction range is dvx, y direction range is dvy. That is why range dvy means velocity changes from vy to vy plus dvy. How can you find the range? If we subtract one from other, then you get the range. Then the same thing, z is dvz. So the number of molecules having velocity component lying between range dx, dvy, dvz, and dqv, that is the three-dimensional element in velocity space. Okay, in velocity space, the coordinates are represented by only velocity vx, vy, vz. So n is the number of molecules. Now see, this result shows that the probability that a molecule has velocity between v to v plus dv decreases exponentially with v. That's why it decreases exponentially with v. Here in the expression, the exponential is e to the power minus bv square. This is the exponential function, you see. Okay, since the negative exponential is there, so we can write 1 by e to the power bv square. 1 by e to the power bv square. So when v increases, now e by v square increases and 1 by e bv square, that is decreases. So the probability decreases exponentially with v. Since the exponential function, so the decrease is exponential. The distribution of, now see the distribution of molecular speed. Molecular speed, now we have three category of molecular speed: RMS, VRMS, and here it is the average velocity, RMS velocity, average velocity, and the most probable velocity. Okay, so when we draw the distribution of molecular speed with this distribution function, the graph is like a parabolic shape. So it is increases, slowly increases, attains a maximum value at a certain velocity, and then it is decreases. So the most probable speed is the speed at which Maxwell distribution function is maximum. If we draw, so the graph, and in graph it will be very clear. Similarly, the number of molecules of Maxwellian gas with energy in the range E and E plus dE. So range is dE. So the number of molecules in the energy range, this expression is there also, dNE equal to twice n E by pi to the power 3 by 2, 1 by kt to the power 3 by 2 e to the power minus E by kt dE with energy now E. See, here is the energy and n is the number of molecules, k is the Bose constant, T is the temperature, absolute temperature. So all these things are almost constant. That is why you can say the number of molecules with this energy range is exponentially connected to the E by kt, e to the power minus E by kt. Okay, so the number of molecules also falls exponentially, decreases exponentially. The average energy of a molecule obeying Maxwell's law E bar, average energy of a molecule is 3 by 2 kt. K is the Boltzmann constant. And from the finite width of spectral line constitutes an indirect evidence in favor of Maxwell's law of distribution. Since if we find the spectral lines coming from the any mercury lamp or sodium lamp, you see that spectral lines, so many spectral lines, but they have a finite width. In the when the lights coming from the mercury lamp, they will pass through the prism, you can find the spectrum, right? Or you can use the spectrometer to study the spectral analysis. spectral lines. They have a finite width. So,
Sir, sir,
huh,
sir. In spectrum, how many lights we can find?
in case of sodium, you can find also two lines. Sodium D1 line, sodium D2 lines. In case of white light, you find you 7 colors in
Seven
the
colors line.
okay,
Yes, sir.
seven
Yes,
seven lines for different colors in visible range. That is
yes,
also in visible range. Okay, we can
yes,
use
sir.
the spectrometer. You can use the grating is more helpful because the spectrometer is only useful in the visible range for 7 colors which you can see. Okay,
Yes,
for
sir.
invisible range, that is red, infrared or ultraviolet or other ranges, you can see that is grating is more helpful. Okay.
Yes, sir. Okay, sir. Thank you.
Unit 3, now we are entering to the unit 3, mean free path. Now see, we have just 10 minutes left. We are trying to complete it. Then another 3 more chapters are there. Okay, mean free path and transport phenomena. Now see, when the particles can already mention in the kinetic theory, also in the Maxwell's postulate, the molecules travel along a straight line before they colliding with another molecules. That means in between two successive molecules, the molecules two successive collisions, the molecule travel along a straight line. Now, if we want to the mean free path, then suppose we follow so many molecules, how many free path they covered in between two successive collisions. Suppose you have 10 molecules, then you find 10 free paths for 10 molecules. For 10 successive collisions, 10 molecules travel 10 free paths. Then you take the average, right? And take the average. That means add all these free paths and divide by the number 10, then you will get the mean free path, that is average distance between two successive collisions by a molecule. Now see, what is V bar? V bar is the average velocity. That means a molecule can travel with this velocity. Suppose in time t that is written in the expression, you see lambda, the symbol of mean free path is lambda. In time t, the n number of collisions, successive collisions occur. N collisions occur. So we have n free paths. Now, how many distance is covered? Now, the velocity into time, that will give you the total free path that is covered in n collisions. Okay. So this is the total distance traveled, and this is the total number of collisions, total number of free paths. Then divide them, and you will get the mean free path. And we write this as V bar tau, the t by n. So in the n free paths take, or n successive collisions take time t, then one successive collision take t by n. You can say this is the time period of the collision. Time period of the collision. For one collision, we take this much of time. And if we divide this 1 by tau, that will give you the collision frequency. We write in the symbol Pc, collision frequency. Okay, in the zeroth order approximation, when only one molecule is in motion, we consider that is not the actual case. One molecule is motion, so many molecules they are traveling in the motion. So in that case, the path, mean free path, found to be V bar by Pc, which is equal to 1 by pi d square n. Okay, this pi d square is equal to sigma, and that is equal to microscopic collision cross section, where d is distance between the centers of two molecules, they which are in contact with each other. So when two molecules are in contact, and you find the distance between the two centers, that is the d. Now see, and n is the number of molecules per unit volume. Okay, and n sigma is called macroscopic collision cross section. Sigma is called microscopic collision section. N sigma is called the macroscopic collision cross section. In the first order approximation, we can write also lambda by kt by sigma p. When p equal to nkt, then p equal to nkt, we have n equal to p by kt, n of p by kt. Then you put the value in this place, you will get lambda equal to kt by sigma p. P is the pressure. Okay. The first order approximation, here all molecules are in zeroth order approximation, we take only one molecule. In first order approximation, we take all molecules are in motion. Okay, then when all molecules are in motion, the collision frequency Pc equal to 4 by 3 n sigma v bar, and lambda c is the the mean free path which is derived Class-1, that is equal to 3 by 4 n sigma, which happen to be 0.75 kt by p sigma in values n sigma. Same thing in the Maxwellian case, we find this is equal to mean free path equal to 1 by root 2 n sigma, which happen to be 0.707 kt by p sigma. If we divide lambda m, mean free path of Maxwellian gas, and that derived by the Class-1, then lambda c equal to 0.n4. Now distribution of free path. Now distribution of free path consider karuchi. Now you take for a sample of n0 molecule, the number of molecules which travels a distance x without making any collision. So that is the free path. This is given by the survival equation. That means when no collision takes place, we say the molecule is survived. So the survival equation is the number of molecules which travels distance x without collision is n0. If we have a sample of n0 molecules, amaro 15 molecule, 15 molecules we have, but 5 molecules travel distance x without collision. So we put 5 in place of n and 15 in place of n0. Then exponential x minus x by lambda. X is the distance and lambda is the free path. Now, so important transport phenomena. So this is very important, and we have 3 transport phenomena are there. Now see, when a gas is endowed with the mass motion, random molecular motion can lead to transport of energy, transport of momentum, and transport of mass. Why transport of energy? Why molecules move? Now see, because if you find suppose in a gas, in some region, inside the container you can say also, in some region the temperature is more than the other region. When the temperature is more in one region, the molecule from high temperature region will automatically flow to the low region in order to maintain the thermal equilibrium. Now see, so due to the temperature difference, when the molecules will travel from one region to another region, they carry the energy. That means the energy from one region is transported to the another region. You can say that is the higher temperature region to the lower temperature region. So that will lead to the thermal conduction. That means how the heat is conducted, thermal energy is conducted from one region to another region. That will give you expression for the coefficient of thermal conductivity. We write the expression in the lower, coefficient of thermal conductivity. The thermal conductivity is because shows the energy is transported from one region to another region. Similarly, the transport of momentum, you can find that some region, the if you imagine that when the gas will flow, that is there is they flow in different layers, the one layer travel with different velocity with respect to another layer. So because of cohesiveness by cohesive force, the layer which travels with low velocity, they start to pull down the layer which travels with high velocity. So because of this frictional case, the viscosity will arise. So when there is relative motion between the different layers of the gas, the viscosity will come. That means we can say the momentum of one region is transported, one layer is transported to the other layer. The the layer which travels with more velocity, that will transport the momentum to the layer which travels with less velocity, right? So that is how the transport of momentum will lead to the viscosity. That is why we also find the coefficient of viscosity of the gas. Similarly, transport of mass, you may find that the some region in the gas has more concentration than the lower concentration than the other. So the mass will move from higher concentration region to the lower concentration region. That will lead to a diffusion. That will lead to the diffusion. We also derive the expression for coefficient of diffusion from that. So we write the expression for the, yeah. So the in case transport phenomena, with three phenomena or three quantities we are to be transported, that is energy, momentum and mass. Energy will lead to the thermal conductivity, momentum lead to coefficient of viscosity or viscosity, and the mass lead to the diffusion process. And for them we will derive expressions for this coefficient of viscosity, that will come out to be 1 by 3 mn bar lambda, or m 1 by 3 Mn. N is the number of molecules per unit volume, m is the molecular mass. So you find Mn is the density. Okay, V bar into lambda. For Maxwellian gas, it is N equal to 2 by 3 sigma, expression is there, mkt by pi. So it shows that the coefficient of viscosity is directly proportional to the square root the temperature, absolute temperature, and independent of pressure. That means with temperature rise, viscosity increases. Now see, the thermal conductivity is given by F by 6 K equal to F by 6 N V bar lambda Kb, where you know it is the F is the only the number of degrees of freedom. Kb is the Boltzmann's constant, lambda free path, V bar average velocity, N is the moles, molecule number of moles. The coefficient of diffusion D, coefficient of diffusion D, that is expression comes out to be V bar by 3 lambda. Okay, so it is 0.376 sigma kt to the power 3 by 2, then P into square root of m. P is the pressure, right? We can find from the if we put the expression of V bar and lambda, then we can reach at this conclusion. See, then unit 4 is the Brownian motion. Brownian motion, that is the irregular and random motion of particles suspended in a viscous solution. Okay, you have a viscous solution. When the particles suspended in it, they will move randomly and irregular manner. This motion is known as Brownian motion because it was first discovered by the Robert Brown, the scientist Robert Brown. And the sedimentation and Johnson noise, they are the very clear example of the Brownian motion. Sedimentation is the process of down of sand. If you take some sandy water in a glass jar and you find after some time the sands will settle down at the bottom and the water above it. This process is sedimentation, and similarly in the noise, when the current will flow through a conductor, there some electron collide with some normal noise which take place, because when electron travel from one higher, lower potential side to the higher potential side, they undergoes collision also. Because of this collision, a noise, thermal noise will come, that is called Johnson noise. So in the, to explain the Brownian motion, then we have theories. One is Einstein theory and Langevin theory. It's a very remarkable theories. Einstein, maybe Einstein also this theory of Brownian motion, he also uh, went to the Nobel juries for a Nobel Prize. Also, though Einstein got the Nobel Prize in photoelectric. Einstein gave a exact description of Brownian motion in terms of the effects of random collisions between molecules of the liquid and suspended particles. He calculated mean square displacement of Brownian particle, equating the expression for diffusion of coefficient D, coefficient diffusion D from random motion of suspended particles and from osmotic pressure difference in different parts caused by difference in concentration of suspended particles. So Einstein derived expression for L square from the expression of D. He find out expression of D into one from random motion suspended particles and two from osmotic pressure. They equate the expression of D deriving from these two and to find out an expression for the mean square displacement, that is L square. L square, this L square equal to kBT by 3 pi eta R0 tau. Kb is the Boltzmann constant, T is the absolute temperature, eta is the coefficient of viscosity of solution, and R0 is the radius of the suspended particles. Now see, which one is a Brownian particle? The suspended particles in a viscous solution. These suspended particles are known as the Brownian particles. Their radius is R0, and you can see tau is the is your collision time. Then RT, we can write also it at the RT by NA, RT by NA, that is comes from the C, Kb, this Boltzmann constant equal to gas constant by Avogadro's number, Na is there, T is there also on the numerator, and 1 by 3 pi eta R0. This is the historic formula for Brownian motion of by Einstein. Okay. Similarly, Langevin gave a theory about Brownian motion, but the approach is different. The approach is derived expression for mean square displacement, assuming the average force acting on a suspended particle. Average force acting on a suspended particle due to molecular bombardment and a fluctuating component. This molecular bombardment made up of frictional and a fluctuating component. The average of these forces, two forces, he derived expression for this average of force, and he found that when this alpha square tau is much greater than 1, this alpha square is the frequency of collision take, and tau denotes the time for which observation is made. So alpha square tau is much greater than 1, the mean square displacement that is obtained by Langevin, that is equal to that is derived by the Einstein. Okay, so when alpha square tau is much greater than 1, the Langevin theory now agrees with the Einstein's theory. That is, the expression derived by derived for mean square displacement is same. Okay, with the real gas we will conclude. Now, ideal gas equation fails to explain the observed behavior of real gas except at low pressure. The difference we have told you, the ideal gas obeys the gas laws where real gas does not obey. And ideal gas suffers, we say, considers as the elastic collision, but real gas is non-elastic collision. Okay, so van der Waals derive expression for the gas equation for the real gas. So van der Waals equation of state for one of a real gas is P plus A by V square, V minus B equal to RT, where in case of ideal gas we write pressure P into V equal to RT, 1 mole or 1 mole. 1 mole n moles nRT. Okay, this A by V square arises the pressure correction and here volume correction. This pressure correction arises due to the presence of intermolecular interaction, because in case of ideal gas we say the molecules are free. Molecules are free means there is no molecular attraction between the molecules. So the energy is total kinetic. When the attractive force exists between molecules, they must possess some potential energy. Because of Earth attraction, anybody is separated from Earth, you see, that body possesses potential energy, right? Similarly, when the attraction force between the molecules exists, the potential energy factor comes into action. In case of ideal gas, we take the molecules are free, there is no attraction, so the total energy is kinetic. But in case of real gas, we say the intermolecular interaction is present. So when a molecule will collide with, bombard with the wall of the container, the force we expect that must be less than, actually the must be less than that. If we consider there is no interaction, so no intermolecular force, the molecule will, the only one force given by the wall of the container, but actually a molecule is attracted by another molecule, so the pressure must needs correction, that is a V square attraction. And the volume correction is a co-volume. V is the known as co-volume and origin in the finite size of the gas molecules, right? So this is the van der Waals equation of state for 1 mole of gas, and from this we can also know about the critical temperature of a gas, critical pressure, critical volume, all these things. So critical temperature of gas is the temperature above which the gas cannot be liquefied. So gas, that means gas cannot comes to the liquid state. So by applying any amount of pressure, so the temperature above which gas cannot be liquefied, whatever pressure you may apply is the critical temperature. Similarly, at critical temperature, not above critical temperature, at critical temperature, the minimum pressure required to begin liquefaction. So you have some gas, you keep them at critical temperature level, and you now start increasing, you decreasing the pressure, you see at what pressure, minimum pressure, the the gas starts liquefying. So if the pressure is below that, then no liquefaction takes place. If pressure is above that, liquefaction can take place. So the minimum pressure at which a gas starts liquefying at critical temperature, then you have to keep the gas at critical temperature first, then you check the pressure, you decrease the pressure, you see at up to what pressure the gas can liquefy. If the pressure is below, the no liquefaction takes place, and the volume corresponding to the critical pressure and critical temperature. So you keep the gas, the temperature and pressure of the gas at critical point, and see what is the volume, and that volume is known as the critical volume of the gas. And the expression, this expression RTC by PCVC, this referred to as critical coefficient of the gas. Okay, so Van der Waals equation reduces to per-phase equation at low pressure. Another thing I forget to write, that is the Penny's experiment, that will derive the Avogadro's, the value of the Avogadro's number, where you can find out the mass of the atom, right? Similarly, the critical constant of Van der Waals gas are given by Pc equal to critical volume 3b, Pc equal to critical pressure equal to A by 27 B square, critical temperature 8A by 27 RB. So with this we can conclude, we have already advanced 10 to 20 minutes to complete this. So 10 people are there now. So anything to ask? And Shilpa, you are raising hand. Shilpa,
No,
you are
no.
raising
Yes,
your
sir.
hand.
Yes, sir.
Okay. Any question?
Sir, now I have no question, but I find my questions in Igyanko's course so that I after ask any question.
After learning, you can ask. Okay, okay, okay. Okay.
Okay.
See, in the Tuesday,
Sir,
we will
sir,
take uh, uh,
one question, sir. Sir, can you find me any important topics in this block for exam?
no, uh, no, all are important for you. Okay.
Yes, sir. Yes, sir.
No particular important question can be. Okay. All are important for you.
Yes, sir. Yes, sir. Okay, sir. I can ask later any
You see,
question.
you go through the question pattern. Okay.
Yes, sir.
And you see what are the subjective questions and what are the subjective how subjective questions are there, and in previous examination which questions are coming, you may follow up that.
Yes,
Okay,
sir. Yes, sir.
otherwise all are important for you.
Yes, sir. Thank you.
Okay, so with this now we can conclude the class. So we have to leave now, right?
Yes, sir.
Excuse me, sir. Sir, excuse me, sir.
What?
Is there any possibility that how can sir notes, sir? Can you share notes, sir, through our email? If we will send email to you, sir, or shall we make any WhatsApp group for it, so that we'll get the notes what you are telling us, and it will our comprehension and we can easily understand.
Okay, you see. Mute your microphone. Mute your microphone. Manas, mute your microphone. Okay, you see, you have 4 units. Is it easy to make a note 4 units at a time? No, it is not possible. There are some subjective questions, so many subjective questions in a chapter also there. 3 to 4 subjective questions in many in one chapter may come, or 2 to 3 questions comes. Then another thing is important, formulas. You have to write the formulas, because to solve the problems, you first write the formulas of these all these chapter or a particular chapter, and clearly mention the quantities used in the formula. Because when you are asked some problem or given some problem, say problem gives some data. So unless you know what are the quantities that is involved in the expression, you cannot use it. Okay, you try to do such things. And note is not possible in this part. So you try to complete, because you have enough time for it. Also, we do have only one class. And also to prepare notes of all these units at a 4, it is like, you see, it is like a
Sir,
whole course.
sir,
uh,
can you give your number me to doubt any questions to ask you? Doubt clear question.
okay, now I will give you the number, but I may not be able every time for it, because I may
Yes,
be may busy in somewhere sometime
yes,
when you call me. Okay.
yes. Sir.
Okay,
Then
94376
94376
04408.
0
What you
double
can
four.
say, or 08.
Hey, thank you, sir.
Okay. So we may make a WhatsApp group of physics A, and we don't have your numbers, have to add them. So anybody can create the group. Okay, and also we'll send Manas.
Yes, sir.
Okay, but note is not possible in our part now.
Sir, actually, I want to request you that, sir, what notes you are showing through this screen sharing. If you share these notes also, it will be helpful for us, sir. Only these notes
Oh,
what you are
okay,
sharing.
okay. I will send you. I will send you. I will send you. It's available.
Thank you very much.
I I I try to. You see, I have already told you the class cannot be taken easily in this mode of teaching. ये जो distance learning process, in the distance learning process, classes cannot be taken. Just doubts can be discussed. Okay, because 4 units and one class. 4 units, one class is not possible. So you prepare for it and discuss. We want to discuss on these things. So we have also blog there. We can also share blog to you. No problem. If you send your email, I will try to send the blogs that is downloaded from the Gyanakos. Go through it. So we may discuss it. Okay.
Yes, sir. That number, sir, what you have given, that is 9437604408. Is this number your WhatsApp number, sir?
WhatsApp now.
Okay, sir. I think, sir, we will make a number and I will make you admin so that other students they will join in the group, and if any query, anything else, they can share through this WhatsApp, sir.
Okay.
Thank
Thank you. Okay. So now we'll leave the class now.